Okay, so we'll do few numerical problems. I think we have just introduced the basic of the three-phase. So we'll try to do some numerical problems that will give us more insight into three-phase system. So first problem here is three loads, each of resistance 30 ohm, are connected in star to a 415 volt three-phase supply. Can you draw quickly what it would be look like? It's a star connected and line voltage, and identify the line voltage and phase voltage, all the different quantity you can just identify. No, star is star, delta is delta. So you start first, then I will do it. Yeah, Y and star are the same. Did I mention in the class that Y and star are the same? So star looks like Y. So if you draw the star, I can draw it here. So if you draw a star, so how to draw a star? We can draw in two ways. One is this way, annotation. Where is the annotation? Can I add something? Yeah. So if I retry, should I draw? Should I draw? Or so if you draw a star, so what is the if you take a look of the physical, how we can draw? Say I have three components. So three phase, each of them is given as 30 ohm. And then I can have another one here that will be of 30 ohm. And then I have another resistor here that will be of 30 ohm. Now, whenever we are talking about star connection, that means one of these terminal, one of the two terminal from each of the component will be commonly connected. So that means I can take this one. I can take this one as common connection. Just take. So I can make this one as a common connection. So this one will be connected here, and this terminal will also be connected here. Okay. So this is the physical. If you want to do in the lab or in the practice, that is how it look like. You have to make one of the terminal connected. Now in graphical representation, we can represent this way. So it would be look like one of the terminal here common, and then we have another terminal here, and then I have other branch here. So I can consider this is 1, 2, 1, 2, and 1, 2. So that means number 2 of all the terminal. It doesn't matter for the resistance, so or the passive element. So it's the same. So any of the terminal you can make common, and the other terminal will be open, that will be connected with the line. So it can be connected to phase A, B, and C. All right. Now this one, if you compare this one, this connection, this looks like an Y, right? So that's why it is called Y connection, or also star. If you consider this one, it looks like a star having so many radiation from the star. Which one? This one, this one, this. Oh, this one. No, it doesn't indicate anything. If it indicates anything, I will mention. There is not no separate different thing. So these are the same. Okay. Now with this one, you have to identify the phase. We have learned 4 quantities of the currents. Sit anywhere. So we can identify 4 quantities for any of the configuration. We can identify 4 quantities. What are the 4 quantities? 2 of them are related to voltage and 2 of them are current, right? So yeah. So one is line voltage, phase voltage, line current, and phase current. Okay. Can you identify in this figure, try to identify all the phase component and the line component? All right. Hmm? No. This is mentioned the load of this connected to a star for 15 volt. Nothing is mentioned. So if nothing is mentioned, we'll always consider line voltage. Okay. If it is not specify anything, then it is always a line voltage. And 415 is a unique number. So if you consider our residential 3-phase supply, that will be line voltage will be 415 always. Okay. And we used to know about 230 volt. What is the 230 volt? 230 is actually phase voltage. So we are taking so whenever you are taking the connection from distribution line, you are taking one phase and one neutral. So that means you are connecting from here, you are connecting between one phase and the neutral. So that is giving you 230 volt. Okay. This 230 volt is, if you convert it to line voltage, then it becomes around 400. But 415 is a very standard value. So line voltage at the low distribution line, it will be 415 volt. Okay, clear? Can you identify what are the different quantities? So which one is marked what quantity? So let us take a look. I'll erase this one and we will add this one to a black line to indicate this is a neutral. So this one is the neutral. So this is the neutral point. So this is similar to your residential, at around residential. If you can see an overhead line, then you will find out these 4 wires. Most of the cases 4 wires, but some cases due to the cost of the wires, they are taking only 2 wires. But if it is a complete circuit, there will be 4 wires. 4 wires means 3 phase, phase A, B, C, or in standard, we can write R, Y, B. So these are the 3 phases and 1 neutral. Now at your home, you need only 1 phase and 1 neutral because you are running 230 volt. Okay, all the appliance at your home, you are running with the 230 volt, and that will be given by 1 phase and the 1 neutral. Okay, but if you are industrial application, if you are industrial consumer, then you are taking all 4 wires. That means 3 wires for the 3 phase and 1 neutral, and then you are connecting to different appliances. Okay, but at your home, you need only 1 single phase and 1 neutral. Now we can identify the line voltage. Line voltage is between the lines, right? So from here, let us take a different color because this is important. If you understand this one, this course is almost, you are done with everything. So this one, so this voltage, what has happened? It's not, take this one. Okay, now this one from this line to this line, this one can be called the voltage YB. Okay, YB, because I am considering this one is the positive terminal. And then we can consider another voltage from here, from this line to this line. From this line to this line, this is VRY. RY, YB, and then we can write down BY, VR. So from here to here, from this line to this line, this is V, BR. Or in simple, we can write down this is the VY, this is VR, and this is VB. Okay. So the voltage we are considering between 2 lines. Okay, that's the line voltage. So I can write down VL is equal to VLL, that is equal to VRY is equal to VYB is equal to VL B BYV and then VBY, right? VBR. So these are the 3 phase, or you can just write down this is simple as VR, VY, and VB. Okay. And in positive sequence, we will learn this one later. So we are writing equal because we are considering this is a balanced. So everything are equal. All the magnitude are equal. Only they are separated by 120-degree phase shift. So each of the relation can be identified as 120-degree phase shift that I will draw later. Now, the next quantity we need to identify is the phase voltage. So phase voltage is in between this line, each of the line and the neutral. So I can identify one voltage from here to here, and that is related to R phase, but it is only within one resistance between line to neutral. So this will be identified as V, and theta indicates this is the phase quantity, not the line quantity. And in between neutral and the phase, which phase, that I can just write down. So this is the phase between red and the neutral. Okay. So this phase is between red and the neutral. This is not significant when we are talking about balanced system because all the quantities are same magnitude. But whenever it is unbalanced, that it will be different. So we need to identify that carefully, that what we mean. So this one between, this is B, that means blue phase and the neutral phase. So this will be identified as, this is also a phase quantity between blue and the neutral. I don't need to write N. Whenever I have written theta, that indicates this is the phase quantity, and phase quantity is always between neutral and one of the line. So that one of the line is mentioned by B, and then theta indicates it is the phase quantity. That means other terminal I am putting my multimeter, the other terminal I am placing on the neutral. Okay. Then the other quantity here, from here, this one, between this C or, so this is Y, right? This is Y actually. So I am just, I'm following RYB. So I will just erase this ABC because that will confuse. So we can write down the same way as ABC. Okay. So then this one would be actually Y quantity. So theta Y, because this is Y. And this one would be B theta, and this is related to B. So either we have to follow the standard is, I can write down ABC phase or RYB. So any one you have to follow. Okay. The standard is RYB is very much standard. So everywhere you will find out this. So we have identified the phase voltage. I have identified the line voltage. Now the currents. Now, if you take a look, is this clear to all of you? All of you is clear? So then the line volt, we will find the values. So before we do that, we try to identify all the, yeah. So so that we are sure that we understand what is meant by this one. So this one is the line current. So this current is belongs to line R. So that's why it will be IR. So similarly, this one, I can just write down, this is IY. And the third one is IB. Okay. And then another current in this particular phase that will be considered as, let's say this is I theta R. This one will be I theta Y. And this one would be I theta B, right? So these are the different quantity. All right. Yeah, Usman? All good? Now we can do the solution, right? It's easy. Can you do? What is the value? Can you find out what we need to find out? Phase voltage, phase current, and the line current. Then we can draw the phasor diagram also. Just continue following from here, then we can see. So here you cannot distinguish actually much because they are actually same, but it is more you can distinguish in delta connection. But the definition is line current is current that is flowing through a line. So if you consider this is your equipment, this is your generator, then it will be at some point it will be connected with the line, right? With the transmission line, or it will be connected with the line to a equipment. So this line that is extended to the line, that is the current that is flowing through that line, that is called the line current. So you are connecting phase through each line, then these are the three current that is flowing through the line to the external devices or the transmission line. Now the phase current is inside this system, inside the generator, you will have the three coils, say three coils, or inside your equipment, there might be three resistance. For this case, these three resistances are connected. So that will be inside a box. So in each of these phase, what is the current flowing? That is the phase current. Okay. So each of these three branches are connected in star. So each of the branch, what is the current that is flowing through, that is called the line current. Actually, I have given the arrowhead in the outward direction, but actually this is a resistive, but current should be inside. Okay. So in the resistive, in the load, current is going inside, right? So to be actual, but you can make the assumption at the beginning. If you do assume, if you are wrong, then you can find out actual value. But here is more obvious that this is a load, and then I can just make the correction of the direction, that this one would be, so I can change this to green, and then this one will be connected to my Y, and then this IR should be in this direction. So similarly, this one would be in this direction. And this one also in this direction, because from the generator, current is entering to this one. So that would be also inside this one. Okay, so current will entering into the load. Okay, so let us just take a notepad to do this calculation here. Okay, so I will draw here again. So we have three resistor connected in star. And we are given the line voltage. So this voltage is given for our case is 415. Okay, so this is the 415, and these are given 30 ohm resistors. So we need to find out the phase voltage, line voltage. Line voltage is given. We need to find out the phase voltage, line current, and the phase current. So these are the three resistors, all are equal. So this is a balanced system. So you can, instead of considering this complex three phase, we can simplify to a single phase. But this is a simple calculation. We can continue in this way. But if you want, you can simplify this one. Now, this is given, this voltage is given the line voltage, right? Between the lines. Now we can find out the phase voltage between this one. So V theta of this one. Okay. So what would be the phase voltage? What is the relation? VL is equal to, what is the relation? which one will they be equal? So it can be equal or it can be different with a factor. So they will not be equal, because if you take a look of line voltage that is connected between two resistors, so line voltage is including two voltage between two resistor, and phase voltage is only one resistor. So they are not equal, right? Do you understand? So voltage between these two lines from here, if you place a multimeter or voltmeter here, and you connect one terminal here, let's say, and then, oh, this is the problem. So I have to share this one. So you should remind me. So I should share this one. Okay. Screen. Okay. Yeah. Now it's okay. So yeah. So this is the drawing. I have drawn the same one. And now it is marked 415 between two lines, right? And two lines, that means it includes two resistor here. So it includes this resistor and this resistor. So this is the whole voltage. So if you add a voltmeter here, that will give you 415. Now if you add another voltmeter, here, let's say here. If you add another voltmeter and you connect between this terminal and this terminal, so definitely that will be different, because this, whenever you measure these 2 points, then it is measuring the voltage across this one resistor, right? So definitely it will be smaller. So we know that this relation is given by a factor of square root of 3. So square root of 3, that means the line voltage is larger. That means if you multiply the phase voltage by square root of 3, then you will get the line voltage. Okay, any line quantity, this is the beauty. So you don't need to memorize these things. So any line quantity and the phase quantity is related by a square root of 3. So you need to identify which one is larger. The line voltage will be, line current will be always larger. So line voltage will be equal to square root of 3 times phase voltage. Okay, we can do the derivation, but we are not interested to do that. But if you are interested, you can come to me, then I can show you how to do that. So we know I know the line voltage, so I need to find out the phase voltage. So phase voltage will be VL divided by square root 3. So that will be equal to 415 divided by square root of 3. And that will be equal to 239 point something, 0.6. So yeah, so that is the voltage. Okay. Now we know the phase voltage. Now we can simplify this circuit and we can consider, as I have mentioned, these three phase, all these three phase has the same resistance. So what we can do, we can simplify, we can draw a simple circuit having one resistance, because that will give me all the values correctly, only they will be separated by 120 degree. So this is my 30 ohm resistor, and this is my neutral I am drawing here. And we identify that this voltage will be equal to, that we have calculated, will be 239.6, right? So instead of having three phase, we have simplified it with a single phase, okay? And that single phase, from this single phase, we can calculate all the values, and we can also draw the phasor quantities from here, because we know the angle difference. Okay, so we can find out from here. The rest of the thing is easy, right? Can you find out the current? So this I can call, this is my current, and this can be phase current. And then we can write down the line current. What would be the value? So it would be I theta would be equal to simply 239.6. And here, if you want, you can start adding the angle, the polar quantity. Here, nothing is mentioned about this angle or the phasor quantity. As nothing is mentioned, I can take this one as a reference. That means with this reference, it is making an angle of 0 degree. Okay. So this one is my reference, and then I can find out the other quantity. Then this one divided by the resistance. Resistance, if you take a look, if you remember, when we have drawn the impedance triangle, then I had the resistance was always in the horizontal line. And then my X was either upward direction or the downward direction, depending on the capacitance and inductance value. So if you consider the upward direction, then this is my X, this is my R, and this is my Z. And then I can write down R is always making an angle of 0 degree. X is making an angle of plus minus 90 degree, depending on upward and downward direction. And then Z will be resulted with a theta. Okay, so I can place here 30 is making an angle of 0 degree. So then if you do this calculation, that will be, what is the value? 7.99 ampere, right? So this is the voltage. So always we have to write down the unit. If you don't write down the unit, your mark will be deducted. So always you have to write down the unit. Okay, so we have found this current, and that would be also, we can just write down this is 0 degree, will also be 0 degree. Okay, so we know the line current, line voltage, phase voltage, we have found the phase current. Now what would be the line current? IL. What would be the line current? For Y, this will be the same because this current is entering, coming here, and this is my line. Here up to here, this is my line current. And then it is passing through, entering to this resistor, that becomes the phase current. Do you think it will be different? So if you apply KCL at this node, then IL would be equal to I theta. So they are same. So I can just write down here, IL will be equal to I theta. And that will be equal to 7.99 at an angle of 0 degree. Okay. Is this clear up to this? Any question? Give me some difficult question so that I cannot answer. In the next class, I need to come back with this, preparing myself. Hard time, give me the hard time. Okay, so this is very simple. So you need to just develop. You have done the single phase. So with the three phase, you just need to accustom with the angles. So now if I ask you, draw the phasor diagram. Now, can you draw the phasor diagram? Say, phasor diagram for the line voltages, phasor diagram for the phase voltages separately. Then we will think about combine them together. So then line current and the phase current. Can you draw the phasor diagram? So when I mention phasor diagram, I have to, the line current, how many line current will be there? How many line currents? So if I ask you, draw the phasor diagram of line currents, how many line currents we have? 3. Yes. So all these 3 line currents should be represented in your phasor diagram. Let me see how many of you can do. If you just think you can, we have mentioned, we didn't do this, but we have mentioned. That's why whenever you practice, that is important. That gives you clear idea. What's your name? I forgot the name. Yeah. Abhishek, are you doing? Lecture note is in front of you. It looks like you are not here. So I will give you some time to think, then I will do it. I want to draw the phasor diagram. Let's start with the line voltages. What would be the phasor diagram of the line voltages? So all value will be the same because we have considered this is the balanced system. Okay. So voltages will be the same. Only difference is the angle. So what is the angle difference of three-phase system? 120 degree. So we have to just place it in 120 degree. So we can consider, say, phasor diagram of line voltages. Of line voltages. Or we can start with the phase voltage. I think phase voltage will be a good way to explain. Let us start with the phase voltage. Okay, I want to draw the phasor diagram of phase voltages. So how many phase voltage do we have? We have V theta R and we have V theta Y. Yeah. You can put all of them in one. Yeah, it should be all the phasor quantity should be in one. And later on, we will put all the line quantity and the phase quantity in one. Okay. So then we will have V theta B. Okay. And we have to take one of them as a reference. Nothing has mentioned. So one of them I will take as a reference. So magnitude is all 415. And I will take this one as my reference 0. Then this one would be, now if I draw the phasor diagram, then we will have the RYB sequence. We will always consider, if nothing we mention, then it will be RYB sequence. This is called the positive sequence. That will be sequence. So that means I will have R phase. So VR. And then next one would be 120 degree. So this is 415. And Y would be 120 degree away. So it would be plus 120. It should be minus. So this would be minus. Usually RYB, we are considering this is 120 degree. Minus 120. So that means you have to go in clockwise direction, another 120 degree to find out your, so this is theta, right? So we are considering theta R. And this will be your theta Y. So I have to go minus 120 degree in the clockwise direction. This is standard practice that RY, it will be always RYB sequence, and from R, Y will be 120-degree clockwise direction. It will make an angle of 120-degree in the clockwise direction. Then we will have this one. This is called V theta V. And this will make another 120-degree minus 120-degree. So that will be equal to 415, an angle of minus 240. And minus of 240 can be written as plus of 120. So I can just write down 415, making an angle of 120-degree. Okay. So all of them are same. So that's why we don't need to worry about. Now, is this clear? So this is simple, right? So we have to just remember the sequence and then place accordingly each of the line according to the sequence R, Y, B. So R, Y will be 120-degree lagging, then B will be 120-degree lagging. So that will be R, Y, B. Now about the phasor quantity. Now we can draw here the phasor, the circuit itself, and then try to explain the relation, how we can find out the phasor quantity. So we have this line, and then we can have this line. So we want to find out between R, Y, and B. Okay. So if you consider, this is very small space, but we can write down VRY is this one, VRY, right? And I have written RY, that means I will consider, we know that there is no polarity for this and no distinguished polarity for sinusoidal. Every half cycle it is changing, but we will consider only the positive cycle, let's say positive cycle. Then I can consider this one will be my positive terminal and this can be my negative terminal. Okay. And from this positive terminal, the current is flowing in this direction. Then I will have this one is the positive and this one is the negative, right? So these are the resistive quantities. So current entering, so current will enter in this terminal. So this will be, current will be flowing in this direction, I theta R. And due to this one, I will have the voltage here, will have positive terminal here and negative terminal here, and this will be V theta R, right? Right? So similarly here, I will have the current here, and then current will be entering in this direction. This is I theta Y, and I can consider this is my positive terminal, this is my negative terminal, this is my theta Y, right? Now VRY is my line current, right? So VRY is my line current. So this is equivalent to, I can write down, this is my VR. Okay. So I want to find out this line current, how it is related. How can I find out the relation between the line current and the phase current? Now, if you apply this KVL in this loop, these two terminal looks open. So to apply the KVL, we can assume that we have a voltage source connected here. And that voltage source is having a voltage of VRY. To write down the equation, because when we have discussed that you can apply KVL in a closed loop, right? So it does not look like it's a closed loop. So to apply, you can assume that this is the voltage source connected here. And then you can write down the equation, remove your voltage source. That will be your equation. So if you apply, then what I will have, I can just write down KVL in this loop. So if you start from here, it is KVL. If you start from here, it is minus VRY. Then I will have plus V theta R. And then I will have minus V theta Y. And that will be equal to 0, right? Right? So if you do this calculation, if you simplify this one, then I will have VRY. I have to take on the other side, then it will be equal to V theta R minus V theta Y. Can I write? Can I write? Yeah. I will upload this one so you don't need to worry. So this will be the equation. Now this addition is a vector addition, right? This is a vector addition. You cannot do normal addition, algebraic addition. So you have to go back here. I need to do, this is my vector diagram of my line or phase. And now it is mentioned that I have to subtract theta r, subtract y from theta r, then I will get the line voltage. So in order to subtract, what I have to do, this is my line, the phase current. So this is my positive y, and I have to subtract. So what I have to do, I have to extend this one in the opposite direction, right? In the same value. So value will be the same, but direction will be in the opposite. So this will be my minus B theta Y. Now, if you add them, so if you extend and add them, so this will give you V R Y. Okay, clear? To find out the line voltage, we have drawn this one, the phasor diagram, only the phase voltage showing the relation. The green one is showing the relation of the phase voltages. They are separated by 120 degree. Now, if you draw separately, then you can draw the phase voltage. Again, each of them is 120 degree separated, but actually it will not be the V theta R and V R Y will not be in the same reference, will not be in the same direction. You can see here, we have found this is the line voltage V R Y. V R Y here is the line voltage, right? So I can write down this is VR is similar. So we have to identify the difference. VR is the line voltage and this is the phase voltage. V theta R is the phase voltage. Now, the relation between the phase voltage and the line voltage, numerical relation is a factor of square root of 3, but angle we don't know. But for a AC quantity, I need two things. One is the angle, another is the magnitude. So magnitude we have found with a factor of 3, but angle we have not found. That angle can be found from here. Now, what would be the angle? Can anybody guess what would be the angle from this diagram? Though my drawing is not perfectly all right, but you can guess what would be the angle producing with the reference. The line voltage is making an angle with the reference. So this theta r is in the reference direction, right? This is my reference direction. So what is the angle between these two? How it is 30? Yeah, so this is 120 and this one would be 60, right? So this is a straight line and this is 120 and that should will be 60. And I have these two quantity V theta Y and V theta R are the same amount, right? Same length, same magnitude. Now, if you draw a rectangle and connect a diagonal, then it will be splitting this angle into half because two of them are the same length. Okay. So that's why this will be 30 degree. Okay. Yeah, because they are in same magnitude. But if they are different values, but this angle will be different. But we have taken the balanced, so they are same magnitude, so they will produce the same, the angle will be splitted into half. Okay. So this will be 30°. Now we know this line voltage. We have already found this line voltage. Oh, sorry, this one would be 240. We have considered this one. That was on my wrong. Sorry for that. So this one would be 240, right? 239, yeah, 239.6. So we have considered we have considered the phase quantity 239.6. Okay. So this one is done. Now the line voltage, we have already found the magnitude. Now we can tell the angle. We can write down VRY is equal to VR is equal to 415 now. Now the first quantity, instead of 0, what would be the angle? This is the reference. We have already found this is 30°, so it would be 30°. Okay. So 415 is the line voltage, because this is the line voltage. So we have found this one VRY. We have found the, where did I draw? So VRY we have found between the line, right? We have identified this is the line voltage between VRY and the line voltage. No, line voltage is higher. That we have already found. The line voltage will be higher. So we have started with the phase quantity. We have taken the reference assumption of the first phase, 0°, and then from that phase we have derived the line voltage. Okay. Yep, line voltage will be always higher or equal. So in delta it will be equal. Okay, that we will find out little later. All right, is this clear? Sorry from my side that I have written wrong here, 415. So this is actually phase voltage. Yeah. Yeah. So all are same. All are same. Oh, that would be, yeah. That would be also the same. Yeah, thank you. So that would be also 239. So we are considering all phase first. Then from the phase, we have derived the line voltage, and the line voltage is already given 415. And we know that the relation magnitude or magnitude relation between the line voltage and the phase voltage is with a factor of square root of 3. So line voltage will be always 3 times square root of 3 times higher than the phase voltage. Okay. So we know this one is 90°. Then we can identify the other value. So VYV equal to VY would be equal to, again, 415 will be the same. Now it should be 30° has been shifted. That means this one will be minus of 90° instead of 120°. That will be also shifted by another 30°. Similarly, we can find out VBY, VR is equal to VB, and that will be equal to 415, and that was 240 minus 240. So what was that? Minus 240. So we can write down minus 240 plus 30. So that will be minus 210. Okay. Or we can just write down this is, so it will be shifted further, 120 plus 30. That would be 150. Okay. So it is moving, all the line quantity is moving by 30°. So this one would be 90° here. slightly longer. And this one would be 90 plus 30. So it would be somewhere here. So this is Vy and this is VV. So negative 90, because this is 120 from here and this is shifted. So this 30 and then another 90, that will make 120 of the line, right? So that's why it is minus 90. So that has to be shifted from here. It is to be shifted by 30. So this was 120. This was 120 minus 120. So it is shifting to plus 30. So plus 30 minus 120 plus 30 will be giving. Okay. So similarly 240, that will be also shifted by 30 in the clockwise direction. So you are going in the anti-clockwise direction. This one is making 30-degree anti-clockwise direction. So that has to be from this position, I have to go in the anti-clockwise direction by 30-degree. So that anti-clockwise direction is positive angle. So minus 120 plus 30, that will give you minus 90. So minus 240 plus 30, that will give me 210. So 210 means it is 120 plus 30, that will be 150. Which one? R, yeah. So we are considering VRY. We can also write down, this is the same as VR, the first phase we are considering only. So we can also write down Vy equal to VYB, and VY, we can write down VVR. Okay, so this is the standard symbol that we can use. Okay. All right. Now the current is very simple, right? For this case, we will have very simple diagram because line current and the phase current are the same. So we have already found one of the phase current, line current. So we can just draw the rest of the phase current. All right.
Regarding the line voltage and stuff, can you go down to the bottom here where you showed that equation?
Mm-hmm.
Just explain that.
Yeah, KVL. So we can redraw. So we are considering only this part. Okay. Okay. So if I redraw this one, then it will be look like this is my R phase. And then I will have, I can draw in the other way. So this is my Y. And then we can extend this one. Okay. So this is my R and this is my Y. Okay, and these voltage we are considering VRY or VR. Okay, so this is the line voltage between two lines, RY. That's why I'm writing RY, and instead of RY, I can just write down R. So that indicates this is the line voltage with respect to next sequence, next line. So that sequence is telling RYB. So next one will be Y. So that means this VR means with respect to Y. So whenever I will write VY, that means with respect to next phase, next line. So that is B. So in this way, we can do that. So we can write down any of these. Now, in order to write down the KVL, this is my way of understanding. You can take this one or you can find your way how you will write down. So this is AC. There is no polarity of the voltage, right? There is no fixed polarity. There is a polarity, but there is no fixed polarity of the voltages. That will be constantly changing. Just to make it clear that you understand. So what we are doing, we are taking one of the half cycle. During any of the half cycle, polarity remains same. So we can just consider that we are taking the positive half cycle. In that positive half cycle, I might have positive terminal here and the negative terminal here. Yeah, you can do either, but you have to think carefully what you have assumed, how it will behave. Okay. So in this polarity, if you consider that I have connected a voltage source here with this polarity, then what I will have, this current will come from the positive terminal and that will go in this direction, right? And also this load is actually connected with the generator. So you can consider that current will always coming from this terminal to here. So from the phase, from the generator, so forget about this one. We'll do this one later. So from the phase, all the phases, all the lines, current is entering to the load. So this current is entering into the load. So this is IR and this is IY. Okay. Now with this line current, you have to find out the polarity of the phase voltage. So what is the polarity of the phase voltage? This line current will come here and enter into this terminal. Okay. This is a resistor. So passive element, current entering the terminal will be positive for that voltage across that one. So that voltage is the phase voltage. Okay. So this one is also current entering. So that means this terminal will be positive and this terminal will be negative, and this is my theta y. Okay. So I have identified all the voltages. Now to make our concept clear, that I have to apply a KVL in a closed loop, I can, for the sake of just assumption, we can take this is a voltage source connected here, and that makes my circuit a closed loop. Okay. And then I can apply. So these voltage, I can consider this is the voltage of this voltage source. Now you can apply KVL here in this terminal, in this loop. So if you start from any point, you can start. If you start from here, then if you are going, the first terminal you are looking at, first polarity you are taking a look, it will be minus, and that belongs to the voltage VRY. Okay. And then if you travel across, first you are finding is plus, so V theta R. And then you are coming minus, so minus V theta Y. And that is the all voltages in this loop, that will be equal to 0. Okay. Now if you write down, so this is KVL, but not algebraic summation. This is the vector summation. That is why we have taken the help of phasor diagram to do the addition. Okay, but otherwise everything is same. So I can just take this quantity on the other side. So that will give me V theta R minus V theta Y would be equal to V RY. Okay, so I have taken the other side, that will become plus. Okay, now I have to take theta R is the positive. So that is why whenever we have done the addition, I have kept theta R in the same direction. Because theta Y is the negative, that's why I have extended in opposite direction. Okay, that has given me the negative vector. And then I have added with the rectangle and find out the resultant of those two, because these two, resultant of these two will give me, so these are the vectors, resultant of these two will give me VRY or VR. All right.
So we're using this just for the angle, not for
No, magnitude we already know. Only for the angle.
The V theta R and V theta Y, we're just ignoring the 239 or whatever because we know that the
You can, if you, yeah, if you want, you can do this calculation here with this rectangle, but we already know, that's why I have not shown you with this calculation. But if you want, you can do the calculation. This is the geometrical calculation with the square of everything. Diagonal is equal to two values, diagonal square is equal to, it look like this one. So diagonal square, if you have a rectangle, you can find out the value. Let's say this is C, and this one is A, and this one is B, and this is your angle theta. Then we can find out C square is equal to A square plus B square plus 2AB, I think cos of something. I'm not sure the actual, but it is this kind of equation. You can use that equation to find out that value. Okay. Okay, any question? So I think we have discussed everything about the phasor diagram. If you do this one, then star calculation will be very easy. If you just remember this one, the most of the calculation is similar. You have to understand the concept. We will do few more and then we'll finish the star delta conversion. Okay, all right. Do you need break? Yeah. Go back. And when you come back, we will do the delta of the same value, same circuit, considering delta connection.
Oh, but what about the currents for this one?
Current will be the same because it's the phase and
So the phasor diagram for the current option.
it will be the same. You can draw the phasor diagram.
It will
so
be the exact same as the same.
Exact same, but the phase current and the line current will be the same. So you just need to find out. We have found one of the line, so I can write down this is my R, and this is also my theta R. Okay.
Yeah.
And then the other quantity will be 120 degree apart, so that will be IY or I theta Y. And the other quantity will be this one, that will be I B equal to IB theta, I theta B. So no separate line quantity and the phase quantity because they are the same quantity and angle is also same. Okay.
So you don't actually need to do the phasor diagram because it's balanced.
It's balanced, yeah. Yes.